What we're going to do is we're going to look at a method for how we determine the empirical formula and molecular formula of a compound. One of the ways that we do it is through what's called combustion analysis, where we take some of the compound and we burn it. Now, if the compound undergoes combustion, we know that combustion reaction produces metal oxides or non-metal oxides. So therefore, this could allow us to determine the mass of each element in my compound before it undergoes combustion. Okay, so for example, if I have a carbon-containing compound undergo combustion and it undergoes complete combustion, all of that carbon during a chemical reaction will become carbon dioxide. So therefore, if I determine my mass of carbon in the carbon dioxide produced, then I can determine, I'll know the amount of carbon in the original compound. So, for example, I know this. My percent of carbon is my mass of carbon and carbon dioxide that was produced over the mass of carbon dioxide. Now, I don't know the mass of carbon in a carbon dioxide produced, but I could measure my mass of carbon dioxide. But because carbon dioxide is the molecular formula for the product formed in the combustion reaction, its percent composition is always constant. So therefore, I could also say that my percent carbon in carbon dioxide is equal to the mass of carbon in 1 mole of carbon dioxide over the molar mass of carbon dioxide. And these two percents will be equal to each other. Similar to determining the amount of carbon, I can also use my combustion analysis to determine my amount of hydrogen in a compound. Because when a compound containing hydrogen undergoes complete combustion, we know that all of that hydrogen will be converted into water. And so therefore we can use this and the mass of hydrogen in my water to know that that is the mass of hydrogen in my original substance. And so I can, because my percent hydrogen, mass of hydrogen in water produced over the mass of water produced gives me my percent hydrogen. But because H2O is the formula for all water always, the mass of hydrogen in 1 mole of water over the molar mass of water is also equal to the percent. And again, these two percents are equal. So let's take a look at an actual example of a question. And we'll use those two concepts, even though we may not totally understand them yet, to try and come to a greater understanding and also determine the molecular formula for this compound. So here we have 5 grams of a sample undergoing combustion analysis. We're going to produce some carbon dioxide and some hydrogen. Okay, we know that the molecule has a molar mass of 88.12 grams because of the combustion analysis. So we're going to determine its empirical formula. Now, although we don't know the molecular formula of the compound, we do know that any compound that undergoes combustion reaction is going to react with oxygen. Now, we're saying that we know that our compound contains carbon and hydrogen because I have both carbon dioxide and water produced. And it may contain oxygen. Now, this subscript on oxygen might be 0, in which case it did not contain any oxygen, or it might be something other than 0. And so what we're going to do is we're going to use the information that we have. Now, as always, we should write down our given. So we know that we have 5 grams of this, of our liquid, and we produce almost 10 grams of CO2 and approximately 4 grams of water. So we wrote down our given. Now, let's solve for carbon first, the mass of carbon. Okay, so we know our given information, and we know our two equations. My mass of carbon in CO2 produced over the mass of CO2 produced times 100% is equal to my percent composition of carbon. But my percent composition of carbon is also equal to the mass of carbon in 1 mole of CO2 over the mass of 1 mole. So therefore, I'm going to just do a quick calculation. There's my molar mass of carbon dioxide. There's the mass of carbon in 1 mole of carbon dioxide. Now, because both of those equations equaled percent carbon and the percent of carbon in CO2 is always the same, no matter how much carbon dioxide I have, those two equations are equal. So now I'm looking for this value because that will be my mass of carbon in this original 5 grams. I know this value, I know this value, and I know that value. So I can substitute in, I'm going to manipulate my equation, and I can solve. So what this tells me is that the combustion of 5 grams of my sample initially contained approximately 2.73 grams of carbon. When at 2.73 grams of carbon in my original compound underwent combustion, it became 9 grams of carbon dioxide. We can also begin to solve for the amount of hydrogen because we know that my percent hydrogen is a constant value when we're looking at water, regardless of how much water I have, whether I have 1 mole of water or whether I have 4 grams of water. The percent hydrogen will always be the same. So again, I'm just going to do a quick calculation over here. I'm going to determine my molar mass of water and my mass of hydrogen in 1 mole of water. Okay. Now, because these two equations are equal to each other, because the percent hydrogen is a constant value for in water, I'll make them both equal. I can substitute my known values in. I know my mass of water produced is 4 grams. I know my mass of hydrogen in 1 mole of water, and I know my molar mass of water. So now I'm just going to manipulate, and I can solve. So now I can see that my sample contains approximately 0.46 grams of hydrogen. So now I know my mass of carbon, and I know my mass of hydrogen. And if I just do a quick calculation in my head, this adds up to about 3.1 grams. But I have 5 grams of sample. So that must mean that my sample contains some oxygen. So I can determine the mass of oxygen by my mass, sample mass minus the mass of carbon minus the mass of hydrogen. I cannot use the percent composition equations or analysis that I did because oxygen comes from 2 spots. Oxygen in my compound and the oxygen gas for the combustion reaction. So I can determine my amount of oxygen. So now that I know the mass of each of my elements, I can start to do my empirical formula calculation. And to do that, we'll make our table. Right? So we know our elements, we know the mass of each in the sample. So I'm just going to write those down. Now my first step, as we know, is to take these values and convert them into moles. So I'm going to divide each element by their molar mass. So now I know how many moles of each element I have. Then we know in our empirical formula the next step is to get a mole ratio. To do that, I divide by the lowest number of moles. So I'm going to divide each of these by the lowest number of moles. And then I'm just going to round to the nearest whole number or multiply by a factor. And in this case, I can round both of them. So as a result, my analysis has told me that I have an empirical formula of C2H4O. Now we have to determine our empirical formula, not our molecular formula. And to do that, we know that we first need to get our empirical mass, or the mass of 1 mole of this. So I'm just going to do the quick calculation. And again, molar mass of carbon times 2, molar mass of hydrogen times 4, molar mass of oxygen times 1. I'm going to add them all up. So therefore, this has an empirical mass of 44.06 grams per mole. I know my molar mass. It was given at the beginning. So the factor that I reduced by to go from my molecular formula to my empirical formula is equal to my molar mass divided by my empirical mass. So I'm going to substitute those values in, and I see it's a factor of 2. So what this tells me is to go from my empirical formula to my molecular formula, I have to multiply each of the subscripts by 2. So therefore, the molecular formula of my compound is C4H8O2.